Hey guys, it's Mr. Morrow here. Sorry that I got to be away today. Actually, I'm at a funeral, and so not to be a Debbie Downer or anything, but here's your actual final lesson in precision measurement, and this is in fact your final lesson of math in high school. Let's get started. All right, so we're going to talk about tolerance. This is the third and final lesson here for our unit. And I'll just highlight that this is on page 12 of the book, so page 12 of the 19. Okay, so we can go there, please. All right. So what can we say about tolerance? Well, I'm going to read through the top part of the document. When objects are manufactured, when you build stuff, none of them are exactly alike. Okay? There are always human or machine errors which will affect the product being created. Okay, it's always errors. These errors are overcome through something called tolerance. Tolerance is important because when items are installed or assembled, parts need to fit together in order for the product to work properly. Okay, so tolerance is defined as follows, and this is what we need to circle here. Tolerance is the range of acceptable variations in measurable dimensions for a given situation. Okay, the acceptable variations in measurable dimensions for a given situation. So when I'm asking for a part for a computer or a car or a desk, there can be a little bit of variation in the size of that part. Just imagine the desk you're sitting on, all the parts that go into it. Okay? They're not all identical. Every desk here is completely different from every other desk if you measure enough, if you get close enough to the details. And so the manufacturer who designed the desk needed to provide tolerance, okay? Needed to deal with the error in the creation of their stuff. So for example, the tolerance level in construction of a house would be much larger than the manufacturing of medical equipment for life or death situations. Okay? For a little part that goes into your heart, okay, the margin of error there is a lot smaller than the size of the eave that goes along the edge of your house. All right? So it's important to note that the higher a range of measurements that's acceptable, the higher number of items that can be used. Okay, so if we have more tolerance, we can accept more things. Okay, so for example, at a school, we accept everyone. Okay, our tolerance for a high school is that, hey, your age is sort of in this particular range. Okay, so we have a pretty high range. Okay, if we wanted to get rid of most of you, well, we could say, well, we only accept people who are 17.2 years of age until 17.3 years of age, and suddenly we'd have a lot smaller student population. Okay. Now, when talking about values that are allowed, we can talk about something called the nominal value. This is the actual target value that I want. So the nominal value is the target value for the measured quantity. It's usually halfway between the maximum and minimum values. Okay? And so our allowed tolerance range is the nominal value plus or minus 1/2 of the tolerance. Okay? This is related to measurement, what we just did. Instead of talking about the nominal value in measurement, we talk about the measured value. Measured value. Instead of talking about 1/2 of the tolerance, we used to talk about 1/2 of the precision, or the precision divided by 2. So this is in fact the same thing in essence, the allowed tolerance range. Through some examples, I think this idea of tolerance might make sense. Let's take a look at the first example. Example number 1. If a machine has a tolerance of 0.020 inches and a nominal value of 0.500 inches, write the dimensions with the acceptable range. Okay. Well, we could say that the tolerance here, we would accept 0. We really want a target value, a nominal value of this. You know, that would be perfect. But we'll accept plus or minus 0.020 inches. So we'll accept a little bit of, variation. Okay, we really want 0.500, but we will accept a little bit of variation to the tune of plus or minus 0.020. Okay, so what's the minimum we'll accept? Well, the minimum size we'll accept is 0.500 minus 0.020. So we will accept a part or an object that is 0.480 inches. That's the minimum that's acceptable. What's the max? The maximum acceptable? Well, that's 0.500 plus 0.020, which gives us 0.520 inches. Okay? So the acceptable range, okay, the machine will accept between 0.480 inches and 0.520 inches. Next example. Okay, let's take a look at example 2. A measurement calls for 8.233 plus or minus 0.002. And it's saying, what is the tolerance? Okay? Well, actually, if you go back to the definition, this 0.0, I'm underlining it, sorry. This is supposed to be half of tolerance. So 1/2 of tolerance is 0.002. So tolerance, well, just multiply by 2 on both sides. And we find that tolerance equals 0.004. Example 3. Tolerance and area. So here's what the question says. Find the tolerance level and the upper and lower limits on the area of the given rectangle. Okay, so we have a rectangle with a length of 6 plus or minus 0.5 centimeters and a width of 2 plus or minus 0.1 centimeters. Okay, well, the area is length times width, right? So let's think about it. The length, let's consider that for a moment. The length that's acceptable for us, we will tolerate 6 minus 0.5, that's 5.5 centimeters, to 6 plus 0.5, that's 6.5 centimeters, is tolerated. So the length could be anywhere from 5.5 to 6.5 centimeters. The width, well, the width could be, 2 centimeters plus or minus 0.1. So 2 minus 0.1 gives me 1.9 centimeters. 2 plus 0.1 is 2.1 centimeters is tolerated. Okay, so the minimum dimensions are here. At a minimum, this rectangle has got to be 5.5 by 1.9. And so the minimum area, well, area is calculated by length times width. So I'm going to grab my handy dandy calculator. Here, you can hear it being open. I don't know if you can hear me typing into it. Here we go, 5.5 times 1.9 gives me a minimum area of 10.45 centimeters squared. Okay, we will tolerate an area of 10.45 centimeters squared. Now, I'll switch colors to green. What about our maximum? Well, our maximum area, I'll just write max area, could be 6.5 by 2.1. 6.5 times 2.1 gives me 13.65 centimeters squared. So the area that we will tolerate is from 10.45 to 13.65 centimeters squared. Okay, I'm not going to answer that last part, so let's just move on. Okay, now this is a final fun question. The diagram below shows a mold for casting of an object. Casting, you take metal, you melt it down, and you make a part. Okay? So the part is itself going to be 5.7 high, plus or minus 0.1, 10.5 wide, plus or minus 0.1, and deep, the depth, is 4.2 plus or minus 0.1 centimeters. Okay? In addition, here in green, we're going to have a hole down the middle of it. Right here, there's a hole. Okay? How big's the hole? Well, 2.3, and we'll assume by 2.3. It's not written there. Both of them plus or minus 0.1 centimeters. Okay? So there'll be a hole down the middle of this part. And so here's the question. Find the upper and lower limits of the volume of material that will be required and the tolerance. Okay. Well, how much volume is there? Well, how do you calculate that? Volume is going to be length times width times height. But how do I calculate this here? What is the length, width, and height that we need? It's not 10.5, 5.7, and 4.2. That would be ideal. But we'll have a minimum volume, and we'll also have a maximum volume. Okay. So at minimum, we'll start with the height. Right here. That height is 5.7 plus or minus 0.1 centimeters. That means that at a minimum, the height is 5.6 centimeters. And at a maximum, that height is 5.8 centimeters. That's the height. Times, well, what's the other dimension? Well, I guess this width over here at the top, 10.5 plus or minus 0.1. So we'll tolerate at a minimum 10.4. And at a maximum, we'll tolerate 10.6. And then finally, what's the depth of this object? Well, 4.2, but plus or minus 0.1. So at a minimum, we'll tolerate 4.1. And a maximum we'll tolerate is 4.3. So that's how much volume would make this block. And then we have to take away, subtract the hole. Okay, so how big is the hole? Well, the maximum possible size of the hole is 2.4 by 2.4 by 4.3. And the minimum size of the hole is 2.2 times 2.2 times 4.1. Now wait a minute, you say. You must have drawn those in the wrong spot. I put the maximum value for the hole on the minimum line and the minimum value for the hole on the maximum line. Well, that's because the hole is absence of material. So if I want the smallest possible size, the minimum volume, I have to ask how much is the most that I could take off of there. And if I want the maximum volume, I have to ask, well, how much is the most that I could take off of that? Or the least I could take off, sorry. Oh well, hopefully that made sense to someone. In the end, from here, all you'd have to do is type that in and you are done. You've calculated the minimum volume of material needed and the maximum volume of material needed. Okay, I hope that helps, guys. I've assigned a few questions with your lovely substitute teacher, and so work through those. Okay, good luck. We'll see you on Wednesday. Bye for now.